Welcome back to my series of lectures on stellar evolution. In this last lecture, lecture number 6, I will be talking about stellar black holes, their formation and concepts like accretion disk, Schwarzschild radius, event horizon and so on. Now let's begin with a basic question. What happens to a supernova remnant if its mass exceeds, let us say, around 8 solar masses? We saw that for low mass stars, the end stage would be a white dwarf. By low mass, I mean if masses are less than around 3 to 4 solar masses, the end stage would be a white dwarf where electron degeneracy pressure counteracts gravity and prevents the contraction of the core any further. But if the mass exceeds the Chandrasekhar limit, then electron degeneracy pressure cannot really, kind of counteract gravity, and the Chandrasekhar limit is just around 1.5 solar masses. To be more precise, 1.42 solar masses. So if the mass of the core at the end of the red giant stage or mass of the remnant at the end of the red giant stage exceeds the Chandrasekhar limit, that's 1.42 solar mass, and goes up to, let us say, around 5 to 6 solar masses, then the contraction continues until a new kind of pressure coming from neutron degeneracy pressure can halt the collapse, and the star basically becomes a ball of neutron. So that's a neutron star. It's a huge celestial nucleus, and most of these neutron stars rotate, and they also emit electromagnetic pulses, which is called as the pulsars. The question is that as far as neutron degeneracy pressure is concerned, even though there is no sharp upper limit or a boundary like the Chandrasekhar mass limit for neutron star, typically around 7 to 8 solar masses is the upper limit. So if the core, or rather the remnant at the end of the supernova explosion, is exceeding this 7 or 8 solar mass, then even the neutron degeneracy pressure is not enough to counteract gravity, and so gravity will start compressing that matter even further to smaller and smaller volume. In fact, this will go on until the object goes into what is called a singularity in space-time. The entire mass gets concentrated into one single geometric point. It's a very amazing exotic object. So this particular point in space where all the mass has now been contracted into is known as a stellar black hole. The reason it's called black hole is the gravitational field due to this exotic object is so intense that even photons or light cannot escape from this object, and hence you cannot really see the object by any radiation that comes out of it. So it's obviously called a a black hole. Remember, photons have a speed equal to c, which is 3 into 10 power 8 meter per second. So the gravitational field around this singularity is so strong that this field prevents even photons from escaping from this very distorted space-time around this object. Nothing can really escape from this object. No information that will ever come out of this black hole. So how do we see the black hole? How do we know they exist? Now these are questions we are going to tackle in the next few slides. Now before that, let's go back to a little bit of history. We all know about escape velocity. You know, if you take the Earth, then the Earth has a gravitational pull. If you throw an object of mass small m with a certain velocity v, we know that it travels up, goes to a certain height, and then returns back because of gravity. One could ask the question, what should be the velocity with which one has to project an object of mass m from the Earth's surface so that it does not come back to the Earth at all? In other words, it escapes the gravitational pull of the Earth. This velocity, minimum velocity with which an object must be thrown from the Earth's surface to escape the Earth's gravitational pull, is called the escape velocity for the Earth. And how does one calculate it? By simply equating the kinetic energy required to escape from the Earth's surface to the gravitational potential energy on the Earth's surface. So if you consider a mass small m and mass of the Earth to be capital M and the radius of the Earth to be capital R, from this equation half m ve squared equal to g mm by r, one can estimate what should be ve. Alternately, one can even rewrite this expression and say what should be the radius of an object of mass m whose escape velocity is ve. So this is a well-known classical expression. In the late 18th century, Michel and Laplace asked the following question. They posed the question that, can we find out what should be the radius of an object of mass m for which the escape velocity is equal to speed of light? That's very simple. In fact, all that we need to do is substitute VE squared as C squared. In other words, the question they asked is, what is the value of R if VE equals C? And you know the answer must be 2 GM by C squared. Now, it's an interesting equation and it has a very interesting anecdote to it. We will see why I've made a reference to this. I would urge you to use this equation to calculate what would be the radius of an object whose mass is equal to that of the Earth if the escape velocity is c, and check out what should be r. Or you can use any mass and check out what should be the radius correspondingly. As you will see, the expression is very simple. It is simply 2 gm by c squared, where g of course is the universal gravitational constant. Now, how is this related to what I am talking regarding black holes? You see, the idea of black holes actually is a consequence of general theory of relativity, which was proposed by Einstein way back in 1915. General theory of relativity, for those of you who do not know, is the most complete theory of gravity. It is much more comprehensive than the Newtonian gravity. So, in the early part of the 20th century, that is around 1916, the German mathematician Schwarzschild, he solved the equations of general relativity and arrived at its solution. Now, when he did this, he obtained an expression which is exactly the same as was obtained by Michel and Laplace for the radius of an object whose gravitational pull is so strong that even photons cannot escape from it. So let me tell you that once again. What did Schwarzschild do? Schwarzschild was trying to solve the equations of general relativity that was set up by Einstein. In one of his solutions, he stumbled upon this idea that if you have an object of mass m, and if this object's escape velocity is equal to that of c, then the radius of that object is given by the equation Rs equal to R subscript s is equal to 2 gm by c squared. This was derived from Einstein's equation of general relativity. This Rs came to be called later on as the Schwarzschild radius. It can be defined as the radius of an object whose gravitational pull is so strong that even photon or light cannot escape from it. Now, this is really amazing that this result of general relativity coincidentally and very strangely matched with the result of Newtonian physics of the late 18th century. Of course, the complete concept of Schwarzschild radius is different from the radius that Newtonian physics had thrown up, even though the idea is the same. So therefore, if any particle or photon is located within this radius called Rs, its escape velocity would exceed the speed of light. And since the speed of light is the maximum speed that is attainable, nothing can ever escape this object from within this distance Rs. No information can ever come out of this region within Rs. Since light also cannot escape from such an object, it is aptly called a black hole. Thus, one may define a black hole as an object that is so compact that within a distance equal to the Schwarzschild radius or within a distance equal to Rs, the speed of light also is not enough to escape its gravitational pull. Very simply put, a black hole is simply an object that is so compact that within a certain distance from it, which is in fact the Schwarzschild radius, the speed of light is insufficient to escape its gravitational pull. Beyond the Schwarzschild radius, the black hole will behave like any object with its normal gravitational field. It's only within the Schwarzschild radius that all the exotic properties of black hole really apply. And when you talk of a black hole, you must remember that it is not really an object in that sense that it will have any size. A black hole doesn't have size. The size of a black hole is simply measured in terms of the size of the Schwarzschild radius. Black hole itself is a point in space. It's a geometric point in space. It is more aptly called a singularity in space-time. The entire mass, whether it is 8 solar mass or 10 solar mass, and we will see in some cases there are black holes which are not the end products of stars, black holes which are formed at the centers of galaxies, which can have millions of solar masses. So this millions of solar mass black hole also is basically a geometric point. So when you talk of size of a black hole, we are not referring to the radius of the black hole, as was thought of, as was postulated by Michael and Laplace. When we talk of size of a black hole, we are referring to a distance from the singularity within which this velocity of escape or escape velocity is greater than c. At the boundary, it will be c. So even photons, if they have to escape the gravitational pull, if they are within the Schwarzschild radius, they can't come out. So this boundary from the singularity to a distance rs, all around this singularity, is called as event horizon. The distance rs from the center of a black hole, when I say center of a black hole, it means the singularity point, marks the region from which even photons cannot escape. It is therefore referred to as the event horizon. You understand this? So that is the black hole. Now, it is a kind of boundary. The event horizon, you can think of it as a kind of boundary beyond which, that means within which, no information regarding the events that occur within that event horizon can ever be known to us. Now, we may assume that the entire mass of black hole is actually collapsed to a single geometric point or singularity. One point I would like to stress here is that it has to be noted that outside this event horizon, that means beyond this distance rs, the gravitational field would be the same as that of any other object. So if you have a black hole of mass, say 10 solar masses, within the Schwarzschild radius, all its exotic properties would show up. You can't, of course, see any of these properties, or you cannot see any events coming out of it. But beyond this Schwarzschild radius of a 10 solar mass black hole, the gravity would be as normal as that of any object of mass 10 solar masses. So I will explain this better with the figure in the next slide. In the meanwhile, there are two important things I would like to draw your attention to. Suppose you have a black hole whose mass is equal to that of the sun itself. Then what would be its radius? Of course, by now you must know that an object of 1 solar mass will not really become a black hole. It will actually become a white dwarf. But for the sake of argument, suppose you have a black hole whose mass is equal to that of the sun, then what would be its Schwarzschild radius? It would be as much as just 3 kilometers. So this is very interesting to recall that the sun has a mass of 2 into 10 to the power of 30 kg. Right now, its radius is around 7 into 10 to the power of 8 meter. Right? Now, if the sun becomes a white dwarf, as it would, then it would shrink to a size equal to that of the Earth, around 5,700 or 5,800 kilometers. But if the sun were to become a neutron star, its radius would be something like 10 to 12 kilometers, as much as it would be as big as Bangalore city probably. But if the sun were to become a black hole, which would not, of course, but if it were to become, it would become a sphere of the size of less than Malleshwaram. It would be something, a sphere of radius maybe around 3 kilometers. So incidentally, this is quite useful because one can write a simple formula for calculating the Schwarzschild radius of any black hole in terms of its mass. So that's given by this expression, Rs of a black hole is equal to 3 kilometer times mass of the black hole divided by mass of the sun. So as a simple calculation, suppose I have a black hole whose mass is 6 solar masses. So what would be its Schwarzschild radius? If I put MBH as 6 m0, then the Schwarzschild radius would be 6 into 2.95 or approximately 18 kilometers. There is another interesting feature of a black hole which is often used to detect its presence. This is called the accretion disk. In fact, the concept of accretion disk is not limited to black hole. It can be applied to different objects, mostly stars, even in their early stage of evolution. Now, what is an accretion disk? It is basically a structure. It's a structure that is formed by diffuse material of gas and dust that orbit around a massive central object. That massive central object would be a star. It could be a protostar, it could be a star in the main sequence stage, it could even be a white dwarf or a neutron star or even a black hole. So an accretion disk is basically a structure that is formed by diffused material in orbital motion around a massive central object. Now this central object, as I already mentioned, is typically a star. Now the interesting thing is, when this material swirls around this object, friction will cause the material in the disk to spiral inwards and fall into the central body. And the gravitational and frictional forces will compress and raise the temperature of this material, and due to this frictional effect, there will be radiation coming out of this disk as it swirls and falls into the central object. This radiation is called the accretion disk radiation. The frequency of this radiation emitted because of this swirling motion and falling into the, it's basically kinetic energy getting converted to electromagnetic energy. So the frequency of this electromagnetic radiation will depend on the mass of that central object, because that decides the orbital velocity also. Orbital velocity, speed with which the object is swirling around this central object. Now, in the accretion disks of young stars and protostars, the radiation coming out of the accretion disk will mainly be in the form of infrared or visible, mostly infrared. But when you come to neutron stars and black holes, the radiation from such accretion disks can be in the X-ray region or sometimes even in the gamma ray region. So you can see that here there is a clue to how to detect a black hole. You may not see the black hole directly, but it can be drawing matter from nearby objects or the accretion disk around it, and as the material from the accretion disk falls into the black hole, there will be radiation emitted due to the frictional and gravitational effect, and that radiation would be X-rays. So if you see copious amount of X-rays, large amount of X-rays coming from some point in space where you don't see an object, it's very likely that there is a black hole there, and the X-ray is coming from the accretion disk that is revolving around this black hole. Now, there is no minimum mass for a black hole. Typically, the upper limit of neutron star would be the lower limit for a black hole, and people have discovered black holes of masses 7, 8 solar masses also, and very, very large mass also. The black hole we have been referring to up to now is the end stage of the collapse of a star. Other than this, there are other ways in which black holes can be formed during the Big Bang and afterwards when the universe evolved. When galaxies evolved, at the center of galaxies also you have what are called black holes, which are formed due to a totally different way. I mean, they are not formed due to collapse of stars. They are called supermassive black holes. So basically there are two kinds of black holes, the stellar black holes, which we are describing right now, and the supermassive black hole. Now, as far as stellar black holes are concerned, they are the end stages of gravitationally collapsing stars, which we have been telling so far. And they are basically the star core of stars whose masses exceeded the maximum limit of both the white dwarf as well as neutron star. And the Schwarzschild radius of such black holes is basically given by the expression that I am written here, which is 2.95 times mass of the black hole, stellar black hole, divided by mass of the sun. This expression has to be evaluated in kilometer when both the masses of the black hole and the sun is expressed in kg. Now, the radius of this black hole will typically be around 3, 4, 5 or 10 kilometer, or sometimes maybe up to 100 kilometer, depending on the mass. We have actually detected, the first black hole detected was in a binary star system called Cygnus X1, and this was detected by the X-rays that came from the accretion disk. So that's a stellar black hole. Now here are some pictures to show you, to visualize a black hole. Here you see this singularity, that's actually the black hole. The hole is just a generic term. There is nothing like a hole. I mean, it's our imagination that this is the point where all the mass has collapsed into. So that's a singularity in space-time. And because of the immense gravitational field, it has completely distorted the space-time around this. So up to a distance of Rs from this point, if you imagine a line here, from this point up to a distance of Rs, which is called the Schwarzschild radius, if you imagine a circle of radius Rs, that circle would be the event horizon. And it is within this event horizon that the escape velocity is greater than c. Once you come outside this escape, outside the event horizon, the escape velocity becomes less than c. So matter outside the event horizon can in fact come out. Radiation from outer regions can come out. That is why when matter is swirling and falling into this event horizon, X-rays are emitted from this region. And that is what you see as the copious amount of X-rays that come out of accretion disk. There are various structures. I will not go into this. There is something called the ergosphere, which is a region beyond the event horizon, wherein most of the accretion disks will be swirling and falling into the black hole or region. And when you come much beyond this, beyond the ergosphere, all that you can see is the gravitational effect of a large, very densely or a very, very massive object. Okay, so this, what you see here, is an artist's imagination of the distortion of space-time around this singularity. Here is another picture to make you, understand better. So this black region that you see is actually the black hole. The entire thing is not the black hole. The entire thing that you see here is this region within the event horizon. This boundary is the event horizon, and the singularity is right there at the center. You will not really see it. Around this, of course, you can have other objects that can be, because of the very, very strong gravitational field, you can have other stars which are actually revolving around the black hole itself. And then when these stars actually come very close, matter from this can be pulled into the black hole and they can become accretion disks, and then that matter can fall into this singularity. During this falling, before it enters the event horizon, by then it would be emitting a large amount of X-rays and gamma rays. So you can see, if there is a black hole and matter is falling into it, you can see a region from where X-rays are coming out, but you really can't see any source of that X-ray. You will just see X-rays coming out from a region where it's completely dark, in a very light manner of speaking. So what are these supermassive black holes? Supermassive black holes are black holes whose masses are 10 to the power of 6 to 10 to the power of 9 solar masses. Such black holes are found at the centers of galaxies. In fact, these are called as active galactic nuclei. The nuclei we are referring to is a supermassive black hole sitting at the center of certain galaxies. They power the entire galaxy. There is another name for it is quasar. Quasar basically stands for quasi-stellar radio source. This is how they were first discovered. From these supermassive black holes, you get different kinds of radiation coming out due to accretion disks matter falling into it in the radio wave, X-rays, gamma rays, and so on. So supermassive black holes are not the end product of stellar evolution. They are basically the energy source that powers entire galaxies, and they sit at the center of most galaxies. Our own Milky Way has an active galactic nucleus sitting right at its center. That's a supermassive black hole. It is beyond the scope of our syllabus to describe the formation of such black holes. But incidentally, how do we know the mass of these black holes is 10 to the power of 6 or 10 to the power of 9 solar masses? Simple physics will enable you to do that. See, if you are at a distance r from the center of these active galaxies, galactic nuclei, then you know that the matter at a distance r would be revolving around the center, and the required centripetal force is given by the gravitational pull of the black hole. So if the mass of the black hole is capital M and the mass of the object that is revolving around it is small m, then one can write mv squared divided by r, which is the centripetal force necessary for the object to revolve around the galactic center or the black hole, and should be equal to gmm by r squared. I'm sorry, I've left out a square here. Here the term must be gmm by r squared, where r is the distance of the object revolving with a velocity v around the black hole at a distance r. So when I solve this, mv squared upon r equal to gmm by r squared, I'll get the mass of the object to be v squared into r divided by g. I've deliberately put a capital R here. The capital R written here is nothing but the small r here. This small r should be r squared. So if I know the distance of this object, which I'm writing here as capital R, from the center of this black hole or from the event or from the singularity point, and if I can measure the orbital velocity v, then I should be able to estimate the mass of this black hole. So that's the technique that is used to measure the supermassive black hole's mass. I'm sorry about this error. This should be gmm by r squared, and I deliberately wanted to use the symbol capital R to emphasize that if we know this distance r from the singularity, and if we measure the orbital velocity, both of which can be done by modern techniques, one can estimate the mass of the supermassive black hole. So it's a supermassive black hole. It is also known as active galactic nuclei. So I've written here a little more, and this is picked up from a Google site from NASA. The active galactic nucleus, or AGN, or quasar as it's called, is a compact region at the center of a galaxy that has a much higher than normal luminosity over at least some portion of the electromagnetic spectrum, with characteristic indicating that the luminosity is not produced by stars. That's the important point. The active galactic nuclei, they emit a large amount of radiation, and this radiation is not due to ordinary objects, not due to just ordinary stars. And this excess non-stellar emission has been observed in a wide range of electromagnetic spectrum, from radio, microwave, infrared, optical, ultraviolet, entire electromagnetic spectrum in fact. So a galaxy inside which sits an AGN, or active galactic nucleus, is generally referred to as an active galaxy. Our own galaxy is an active galaxy. The non-stellar radiation from such an active galactic nucleus is theoretically, it is supposed to come from the accretion of matter, which I referred to, due to a supermassive black hole that is sitting at the center of the host galaxy. So this is again an artist's impression of what it would look like. So you have an entire galaxy, and within the center of the galaxy you have this supermassive black hole sitting here, and the accretion disk around it, when it spirals and falls into it, the frictional forces and gravitational pull, etc., which causes electromagnetic radiation to be emitted in various bands of the electromagnetic spectrum, comes out as jet. So that is how this would look. In the initial years of its discovery, first radio waves were discovered from such objects. So people did not know the source or what is the origin of these radio waves. So these objects were called as quasi-stellar, because it was not known whether it is a star that is emitting or whether it is some other object that is emitting. So it was known as quasi-stellar radio sources. So is there evidence of the black hole? Yes, black holes have been discovered. Several of these black holes have been discovered, and the basic evidence is by the accretion disk method that I referred to. Here is again a picture of this. You have a black hole here, and then there is a nearby star. This is another way in which accretion disk can have matter. There is a nearby star, and because of the gravity of this black hole, matter from the star is being pulled, and that becomes an accretion disk, and it revolves around this. And due to this revolution, as matter falls into this, because of friction between the particles, it emits electromagnetic radiation. So this white region that you see is not the black hole. The white region is the accretion disk. The dot at the center where there is no light, that is the black hole. And this radiation is not coming from this dot. It is coming from the falling material. So the best evidence of stellar mass black hole comes from binary star systems, in which one of the stars is a black hole, the other is an ordinary star, in which one star of the pair is not visible to you because that's a black hole. And there is this flickering X-ray emission, which is characteristic of an accretion disk around a compact object. So that's the basic and fundamental evidence that we have. And the orbit and characteristic of the visible star, this orbit, if you know the orbital velocity of this star as it goes around the black hole, one can calculate the mass of this object, and that turns out to be much greater than 10 solar masses, indicating that the second object must be a black hole. So these 3 points put together gives you an evidence. The best evidence, if I read, the best evidence of stellar mass black holes comes from binary star systems, in which one star of the pair is not visible because it's a black hole. The flickering X-ray emission, which is the characteristic of the accretion disk around this compact object, and the orbit and characteristics of the visible star indicate that the mass of this invisible companion should be greater than typically 3, 5, 7 solar masses. So a number of such systems have been found, and even black holes with millions of solar masses have been detected in the same way. Got it. There is a second evidence of a black hole, and that is quite recent. This is the ultimate prediction of general theory of relativity, namely gravitational waves. Actually, when two black holes or two massive stars collide, the collision can result in distortion of space-time and ripples in space-time, which are called gravitational waves. This was predicted by Einstein way back in his theory of gravity or general theory of relativity. It took almost 90 years for the prediction to come true, and in 2017, in fact 2015 I should say, the first gravitational wave was detected by the LIGO observatory, which is acronym for Laser Interferometer Gravitational Wave Observatory. In the year 2015, LIGO discovered, or for the first time, LIGO discovered gravitational waves, which was due to the collision of two black holes spiraling into each other. Imagine, I told you about the accretion disk of one star revolving around the black hole. You can have two black holes revolving around each other, and the gravitational pull will be so strong that eventually they would merge or collide. And when such two black holes collide, or a neutron star and a black hole collides, or when two neutron stars collide, the warping of the space-time would be so much that ripples in space-time would be created. And these ripples in space-time is what we call gravitational waves. And this is direct evidence of not only of the gravitational theory, that is Einstein's theory of gravitation or general relativity, it is also indirectly the evidence of black hole. So in 2015, as I mentioned, for the first time, the gravitational waves from the collision of two black holes spiraling into each other was discovered. And later, 2-3 years later, the other detector, which is the Virgo detector in Italy, they also started detecting it. And since 2015, several such collisions between black holes, between a black hole and a neutron star, etc., have been detected. And we now know for sure that black holes are real objects out there in space. So with that, we come to the end of this series of lectures on stellar evolution. I hope it's been a journey worthwhile for you. I found it extremely interesting giving these series of lectures, and hope that you guys also enjoyed the journey of a star from its birth, its evolution, its middle age, and eventually its death, either as a white dwarf or a neutron star or as a black hole. Thank you very much. More about the universe and the cosmology in the lecture series that will follow. Thank you.